Okay, in the last section of chapter 5.12, we're going to look at the behaviors of implicit relations. We're just going to apply all the things we learned about critical points, increasing, decreasing intervals, and concavity, but in the context of an implicit relation. Okay, so just like before, critical points occur when dy dx equals 0 or when it doesn't exist. You can use the notation y prime if there's only two variables in the equation, because it's clear that it's going to be a y and an x situation. Concavity still depends on the second derivative, which is d squared y over dx squared, or sometimes we write y double prime because there's only two variables, so it's accepted. Okay, now let's look at the first example. It says, consider the curve 3x squared plus 3 equals this. Remember, curve just means it's a graph. Don't worry about the word curve. This is an implicit function because the y is kind of embedded into the equation rather than saying y equals. Okay, it says at negative one half, is the curve increasing or decreasing? When I see increasing or decreasing, I'm thinking, is y prime greater than 0? Is y prime less than 0? So let me go ahead and take the derivative. Since it's implicit, I'm going to do implicit differentiation. So this is x and y. I'm doing it with respect to y, or with respect to x. Oh, it's a hard day. Okay, the derivative of 3x squared is 6x. Since it's respect to x, I don't have to write anything next to it. The derivative of 3 is 0. The derivative of ln of 4y squared is 1 over 4y squared times the derivative of the inner function, so times 8y. And because this is with respect to x, I need to write dy dx, or I need to write y prime. I'm going to write y prime to show you what it will look like. Okay, now do I want to simplify this, or should I just plug it in? Okay, I'm going to plug in. I just want to see if y prime is positive or negative. So I can plug in the point now if I want, or I can wait and plug it in after I've simplified it. It's entirely up to you. Okay, so at negative 1 comma 1/2. Okay, so that's going to be 6 times x equals 1 over 4 times y squared. Y squared is 1/2 squared, is 1/4, times 8 times y prime. Okay, what is this? This is negative 6. This is 1 over 1 times 8 times half times 4y prime. Let me go up here. So I have negative 6 equals 4y prime. So y prime is negative 6 over 4, or negative 3/2, which I didn't really have to simplify it because I just care that it is less than 0. So let me see what the question's asking. Is the curve increasing or decreasing? Okay. Curve is decreasing. If they ask me why, I'm going to say because y prime, or because dy dx is less than 0. Okay, let's go ahead and look at example 2. On the curve x squared minus 3 equals e to the y, is the curve concave up or concave down at negative 2, 0? Since I see concave up and down, I'm thinking I want this second derivative. So, which we can call y double prime, or we could do d squared y over dx squared. But second derivative. This is implicit, so I'm going to go ahead and take the derivative with respect to x and get the first derivative, and then I'll go from there. Okay, so if I take the derivative of this, derivative of x squared is 2x, derivative of 3 is 0. The derivative of e to the y is e to the y, but since it's respect to x, I'm going to write y prime, or I'm going to write dy dx. And now I am going to solve this because I have to do the second derivative. So that's going to be 2x over e to the y. Now I need the second derivative. You absolutely cannot plug in negative 2, 0 until the very end. Once you plug it in, you're going to turn it into a constant function, and the derivative of that is always 0. So don't mess it up. Let me get the second derivative. Okay, so this is my first derivative. Second derivative, I'm gonna have to use quotient rule, huh? Okay. Second derivative equals low d high, the derivative of 2x is 2, minus high d low. The derivative of e to the y is e to the y, but because it has a y, I'm going to put y prime. Square the bottom, and away we go. Okay, do I want to simplify this now? Or should I plug in? Let's just plug it in. Okay, so what are we going to do? We want to evaluate this at negative 2 comma 0. So that's e to the 0 times 2 minus 2 times negative 2 times e to the 0 times, ooh, we need y prime. Okay, so at negative 2, 0, I could plug in the expression. I could plug this expression in here, or I can evaluate it to the side and plug in my answer. I'm going to plug in the answer. So at negative 2, 0, that's 2 times negative 2 over e to the 0, which is negative 4 over 1, which is negative 4. So I'm going to plug in the negative 4 right here. And the bottom, e to the 0 squared. Okay, it looks bad, but it's not bad because e to the 0 is 1. So 1 times 2 is 2. Negative 2 times negative 2 is positive 4 times 1, 4 times negative 14, negative 16. E to the 0 is 1, so 1 squared is 1. So this is going to be negative 14. So the second derivative of y is negative 14. I really just care that it's negative. So what is it asking me? It's asking me, is the curve concave up or concave down? Okay, curve is concave down. If they ask me why, because y double prime is less than 0, or d squared y over dx squared is less than 0. Okay, let's consider one more example. Okay, consider y cubed minus y equals x squared, such that dy dx equals 2x over 3y squared minus 1. So they gave me the derivative. D squared y over dx squared equals 2 over 3y squared minus 1 minus 24x squared y over that thing. So they gave me the second derivative as well. So at 0, 1, is the point a relative max, a relative min, or neither? Well, let's start by just evaluating the first derivative at 0, 1 to see if it's a critical number. Because if it's a critical number, it's definitely a relative max or min, and then we'll figure out what to do about the next step. Okay, so the first derivative, I'm going to plug in 0, 1, which I'm going to write it like this. Okay, so where's the first derivative? Right here. Okay, at 0, 1, that's 2 times 1. No, it's not. It's 2 times 0. So, well, that's going to make it 0. Over 3 times 1 squared, 3 minus 1. So this is going to equal to 0. Okay, since the derivative equals 0, then 0, 1 is a critical number, for sure. If it was not equal to 0, then I would be like, oh, it's not a relative maximum or minimum because it doesn't equal to 0 there, or it's not undefined. If it were undefined, that would help as well. Now, the first derivative test is where we check the intervals on the left and right to see if they're increasing or decreasing. I don't want to use that test because I don't know all the critical numbers, so I'm not sure how to make my intervals. So I'm going to use the second derivative test because they gave me that information, and I'm going to use what they gave me. Okay, so d squared y dx squared, I'm going to plug in 0, 1 at that point and use the information from that to determine whether this is a relative maximum or a minimum, or none. Okay, so I'm plugging it into this expression now. So 2 over 3y squared. 3y squared is 3 minus 1 minus 24 times, oh, x squared is 0. Okay, so it's going to make the top 0. I'm not going to worry about the y. At the bottom, what am I gonna, I'm gonna have 3 minus 1 squared, but as long as it's not undefined, it's fine. So what is that? That's 2 divided by 2 is 1 minus 0 is 1. Okay, now let me think about the second derivative test. I know that at 0, 1, the derivative is 0, so it's a critical number. I know that the second derivative is 1, which means it's concave up at that point. So if it's concave up at that point, then it must mean that that point is a relative minimum. So let me write an answer to the question. At 0, 1 is the point relative maximum, minimum, or neither. Okay, 0, 1 is a relative minimum. Why? Well, because dy dx at 0, 1 equal to 0, that's how I knew it was going to be a critical number, and d squared y dx squared was positive. Actually, I should say at 0, 1, because it's not always positive, but it was at the point. Okay, so based on the second derivative test, it was a relative minimum.